Okay, for these problems, we are going to be simplifying radical expressions that contain exponents. So here, first I'm going to think, okay, if I were to reduce the square root of 8, how would I do that? I would think about it as the square root of 4 times the square root of 2, because 4 is a perfect square number, and it would just be 2 root 2. Well, now I'm going to think about my x to the 4th. Remember, that's just going to be like the square root of 1, 2, 3, 4 x's. We know that x squared is a perfect square, so we want to think to ourselves, how many groups of x squares do we have? We have 1, 2. Each group that I've circled is a perfect square. If I take the square root of x times x, I'm left with x. Here, if I take the square root of this x times x, I'm left with x. So the square root of x to the 4th is x squared. Now, when I write my answer, I don't want to write it this way. I always want to put my rational answer first. So 2x squared is the rational part, and the irrational part is this leftover root 2. Sometimes I like to call these numbers the outside numbers and the inside numbers, because when I'm done simplifying, these are outside the square root and this is still inside the square root. When I look at number 18, I need to think to myself, what number multiplied 4 times gives me 16? And that reduces perfectly to 2. Well, now I've got this x to the 12th, and I need groups of 4. So I think to myself, 12, and that's the last time I'm going to write them all out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 x's, and I need groups of 4. So I have 1, there's a perfect 4th. 2, there's a perfect 4th. 3, I have 3 perfect 4ths within x to the 12th. So the 4th root of x to the 12th is, this is 1x, 2, 3, x to the 3rd. So my final answer for number 18 is 2x to the 3rd. Number 19, I'm taking the cube root of 2x to the 6th. Now, unfortunately, I can't reduce the 2, and it's not a perfect cube, so it is going to remain irrational. It's going to remain inside the radical. Now I look at this x to the 6th, and I think to myself, I have 6 of these. I need groups of 3. Now, the nice thing is that 6 divides by 3 perfectly, and I get 2. That means the cube root of x to the 6th is just x squared. And my final answer is x squared times the cube root of 2. Let's think about that a little differently. I'm going to box this so we remember it's the final answer. We know that the cube root is like a 1/3 power. Think about it. When I take a power to another power, what do? We multiply our powers. So the 2 would just get the 1/3. Nothing really exciting there. But when I multiply 6 times 1/3, 6/3, I get 2. So it's another way to think about it. You can either think about how many groups of 3 do I have, or just do 6 divided by 3, because it's the same thing as multiplying the exponents 6 and 1/3. Now, number 20, I have the 3rd root of 32, x to the 6th. Now, the 32 is not a perfect cube, but it does break up into 8 times 4, and 8 is a perfect cube. The cube root of 8 is 2. So that works. Now I have x to the 6th again, and just like the last one, 6 divided by 3 leaves me x squared, because I have 2 groups. I'll do it one more time. 1, 2, 3, 4, 5, 6. 1 group, 2 group. Because I'm looking for groups of 3. Alright. And I have this 4 left over, so it's going to be 2x squared times the 3rd root of 4. Number 21 is asking me for the 5th root of 32x to the 5th. Now, we look at this and we're like, obviously the 5th root of x to the 5th is just x. Obviously, this is a perfect 5th. But we have to remember that 32 is also a perfect 5th. 2 multiplied 5 times will give you 32. So your final answer for number 41 is 2x. 22 looks kind of messy, and it is. I have the third root of 81, x to the 11th, y to the 8th. Well, I want to remember that 81 is broken up into 27 times 3. And 27 is a perfect cube. If you needed to factor down 81 to 3 times 3 times 3 times 3, that's fine. And then you would realize that you have a bunch of 3's lined up. You'd have 4, in fact. And there's 27, and there's your perfect cube. If you need to do that, that's fine. But I'm just going to remember, eraser, come on. There it goes. I'm just going to remember that 27 divides evenly into 81 3 times. Now I have x to the 11th. I'm going to write my number answer first. So I know that's a 3, and I know I have the third root of 3. All right, now I have that x to the 11th. So one way I'm going to think about it is I have x to the 11th to the 1/3. And I'm going to do something I never do, and I'm going to use a mixed number. 11/3 is like 3 wholes and 2/3. All right? 11/3 is 3 and 2/3 because it's 9, which is 3, and then 2 left over. That means it's going to be x to the 3rd and then x squared left inside. This is where the x to the 3rd comes from, and this is where the 2 left over come from. Another way you can think about it is I have 11 divided by 3. It goes in 3 times, and there's 2 left over. This is what goes inside the radical, and this is how many we have outside. Okay. Now I have y to the 8th. Y to the 8th is going to work in a very similar way. I can take y to the 8th to the 1/3. Think about that as 8/3, and I know that 8/3 is 2 and 2/3. That means I'm going to have y squared and then y squared. Another way to think about it is to say, okay, I have 8. I'm looking for groups of 3. That goes in 2. I have 2 left over. This is what's going outside the radical, y to the 2nd. And inside the radical, I still have y squared. I'm going to give you the visual demonstration of this one more time. I'm going to box this because we're getting very colorful here. This is my final answer. Just to show you with that y to the 8th, 1, 2, 3, 4, 5, 6, 7, 8. I'm looking for groups of 3. There's 1, 2 groups of 3. That's where the y squared outside the radical comes from. And I have 2 left over. I can't make any more groups of 3. And that's where the y squared inside the radical comes from.